Hey everybody, it's Mr. Oliver. I'm going to go over the solution for the AP Physics 1 Unit 6 free response practice problem. This is going to be question number 1. So let's go and get started. Alright, so this first question, got a little mark on there, talks about an object that has 0.125 kilograms and it's going to be set on a spring and set into oscillation. They obtain some data for the position versus position and velocity as a function of time in the graphs. And so if you look at the graph for the position, you get a pretty good, smooth, steady set of data. Now on the velocity time graph, you get these little spiky things. And I think what they're trying to do is to illustrate that sometimes when you take measurements of velocity from using digital lab equipment, kind of like what we've done in class, the data isn't always great, but you can get a general sense. And so they're trying to get you to be able to interpret a graph, even if it's not perfect. And so that's what's going on here. And so for the first question, it says, on the grid below, sketch the potential energy of the object spring Earth system as a function of time. Explicitly label any intercepts, asymptotes, maxima, or minima with numerical values as appropriate. And that's actually pretty critical that we pay attention to that when it says numerical values. So what I'm trying to find is the potential energy of this system. Well, it's a spring mass system, right? And so there's different ways we can do this. The potential energy of a spring mass system would be 1/2 kx squared. That's one way to do it. And so these maximum values of how far it moves up and down, I could express in terms of x. And so if I did that, if I looked at this graph really closely, the center line of this graph is, it's kind of hard to tell, but we can just estimate it. It's about like right here, somewhere around there. That's about the center line. And so that means that the maximum amplitude, which would be x, is the height of this little hump here, or this little trough. All right. And so if I looked at this real closely, x is, I don't know, about, well, it's about 0.2 to here. So this is about 0.7. Let's say about 0.75 plus another 0.2 or hang on. So 0.7 be 5. So that's about 5 and 2. It's about 25 centimeters, somewhere around there, close to it. So I'd have 1/2 times k times 0.25 meters squared. And I could calculate it, but the problem is I don't know what k is. So I got to figure out some other option to calculate how much potential energy I have. Well, because we said in previous discussions that the potential energy can also equal the kinetic energy, because you're always going to, 1/2 mv squared. You can always trade between the two, and that total amount will be equal to each other. So I do have the mass, and I'm given velocity in this graph right here. And in fact, if I look at this graph, the maximum height of this graph of velocity gives me about 1.6. And so what that is the maximum speed is about 1.6 meters per second. And so that'll allow me to find out what the maximum kinetic energy is. So it'll be 1/2 times the mass of 0.125 times 1.6 squared. And that would give me approximately 0.16 joules of maximum kinetic energy, which, if we're drawing potential energy conclusions from that, then that also means the maximum potential energy is also 0.16 joules. So now when I come down here to graph that, I'll know what my maximum value is. And so let's just say that right here is my maximum value. It's going to be 0.16 joules. Okay. Now, here's the thing about potential energy. We kind of need to go back to one of our original graphs that we did on the review practice, where we see that the potential energy always starts at a highest amount whenever the time is 0, because that's when you set it into motion. So that means our potential energy is going to start at some high location right here, and then oscillate between that highest location and zero energy, because you can't have negative potential energy here, through every period. Now here's the deal. The period is 1 second. So that means that I have to start and end in one period at 0.16 joules. But if you look at your original graph of potential energy, this graph, it has not one, but two peaks after the initial peak in one period. So if this is one period here, I've got to actually kind of almost make this W shape for the potential energy in one period. And so that means I'm going to have a maximum as well at this 1/2 second mark, or 0.5 seconds. And it oscillates between that maximum and zero on the quarters. So it's going to be some kind of a shape generally like that. And then we can just kind of go through and fill in this whole thing as a series of alternating potential energies, like so. Okay. Now the second question, part B, says I want to find the acceleration as a function of time. Okay, that's pretty easy, because if you remember, the max acceleration, which would be how high it could possibly ever go, has a real simple form, a omega squared. I'm not going to worry about the negative sign, I'll just worry about the magnitude. Well, our A is this maximum amplitude, which we said was 0.25. And then our omega, we got to calculate that real quick, so I'll come up here and calculate omega. Omega is 2 pi divided by the period. And we said already that the period is just one complete cycle in 1 second. So that means omega is 2 pi. All right. So when we plug that in, we'll just plug in 2 pi, and that's going to be squared. And so when we calculate this max acceleration, we get 9.87 meters per second squared. And just for simplicity's sake, I'm just going to round it up to 10, just because it's a little easier to graph that. And so we're going to have a maximum of 10 and then a minimum of 10, or negative 10, I'm sorry. Now then you got to say, well, what about the acceleration? How do I get what shape this looks like? Well, once again, you can get acceleration by taking the slope of a velocity graph. And we're given a velocity graph up here, and so it starts off with a positive slope. So that means my acceleration would start off with a positive acceleration. Right here at the 1/2 second mark, the slope is negative. So that means at this 1/2 second mark, the acceleration has to be negative. So remember, slope is acceleration. And then you keep doing that. 1/2, or at 1 second is positive, 1.5 it's negative, positive, negative. And so we're going to oscillate back and forth between a positive and a negative every 1/2 second. And then of course where it crosses the axis is going to be right in the middle at the quarters. And so now whenever I graph the acceleration, I've got a nice smooth kind of a cosine shape for the acceleration. Okay, that's for question B. Question C says, next the student is given a rubber band and asked to determine whether the relationship between the restoring force exerted by the rubber band and the amount it is stretched is the same as that of an ideal spring. Describe an experimental procedure that the student could use to collect the necessary data, including all the equipment that the student would need. And so this is going to be real similar to our Hooke's Law lab that we did. But instead of stretching out a spring, we're going to be stretching out a rubber band. And so in a roundabout way, just kind of a bulleted list, what I would do is I'd say I'm going to collect different masses. And use them to stretch a rubber band by hanging it on a ring stand. I'll then record how far the rubber band stretches. And also I'd record the mass for that stretch. Okay, and it's important to note on this question, it says, describe an experimental procedure that the student could use to collect the necessary data, including the equipment. I guess I should probably elaborate a little bit more on equipment, but as long as I understand I'm using a rubber band with some masses and probably strength, put it on a ring stand will probably be okay. It doesn't say anything about how to calculate anything. So this is all you really need for part C. Part D, it does say, how should you analyze the data? Okay, so in part D, I said I'm going to plot the force, which is just mg, on a vertical axis, and the stretch length on the horizontal axis. If the data plots a linear relationship, it obeys Hooke's law. Okay. And so I don't even need to calculate anything. I just need to explain how you're going to do it. So the idea here is that just like we did in the Hooke's law lab, if you plot force versus how far it stretches, and that data shows up to be nice and linear, then yeah, that's a Hooke's law relationship. Because if you remember Hooke's law, the spring force is equal to K times X. That is definitely a Y equals mx plus b looking graph. It's a linear graph. All right. Now part E does say, using the original graph for position versus time, determine the position, velocity, and acceleration functions for the object. So we go back to this, and this acceleration function and determine what my functions are for that. So for the position function, we need to know the amplitude, and we also need to know our angular frequency. So our amplitude, we said previously, is 0.25. Our angular frequency is 2 pi divided by the period, which is just 2 pi, because the period is 1 second, 2 pi over 1 second. And so now I can plug this in. But the problem is, my graph is not a right side up cosine function. Notice how this initial value is flipped upside down. So I actually have to make a negative sign in front of this. So my position function for this particular demonstration is negative 0.25 cosine of 2 pi t. Okay, so that's my position function. Now, for the velocity function, it's typically negative a omega sine omega t. But it's important to look at your graph and look. It's like, hey, this is not an upside down sine function. It's just a regular plain old sine function. Because I have that shape, I can go ahead and look. It's like, hey, it starts at 0 and it goes up instead of down. So that means that this plus sign right here is actually going to be kind of negated because that graph is right side up. And so when we plug our numbers in for a omega throughout this, we end up getting 1.5 sine of 2 pi t. That's our velocity function. And then lastly, our acceleration function, which is typically negative a omega squared cosine omega t. Well, if you look at your acceleration function, you'll see that that graph does start above the axis. It starts in a positive position, so this is your typical cosine shape right here. And so that means that our negative sign here will just drop off as well. So it leaves us with acceleration is 10 cosine 2 pi t. And you substitute your values in. All right, that was part E. And then lastly, part F says determine the spring constant of the original spring. Guys, there's many different ways to do this. I'll just choose one. Part F says we're looking for the spring constant. So for a spring mass system that obeys simple harmonic motion, my term omega, my angular frequency, is the square root of k over m. You could have also done period is equal to 2 pi square root of m over k, because you know the period and you know the mass, so you can solve for k. Guys, there's all different kinds of ways. And the reason why I chose this is just because I happen to know what omega is. It's 2 pi. So 2 pi is equal to the square root of k over m. So when I solve for k, I get 2 pi 2 pi squared is going to equal, or 2 pi squared divided by times the mass. Sorry guys, I can't do algebra. So 2 pi squared times the mass, which is 0.125. You end up getting a spring constant of about 4.935 newtons per meter. All right, and that concludes part F of that free response question. All right, guys, if you have any other questions, please let me know. Just send me an email, and I'll be glad to help you out. Thanks a lot. Have a good day.